and welcome to the EON Products webinar on passive groundwater sampling. My name is Chase Varhol, and I'm the General Manager here at EON, and will moderate today's webinar. EON Products was founded in 1994 with a mission to make environmental sampling and monitoring easier and more cost-effective, and over the last 29 years, we've been lucky enough to help make that goal a reality for thousands of people and projects in the environmental industry. Today, EON specializes in a range of groundwater sampling and monitoring solutions, and we've become the largest supplier of passive samplers for groundwater monitoring in the world. We're very excited to be in front of a group of industry professionals today and discussing something we're so passionate about. A few housekeeping items, and then I'll introduce our speaker for today. You may have already noticed, but this webinar is being recorded. We can send out copies of the recording to those in attendance after the webinar is completed. During this webinar, all participants' cameras are off and microphones are muted. If you do have a question during or after the presentation, we encourage you to go to the Q&A button at the top of the Teams meeting. That will open up a window pane on the right side of your screen where you can type up a question and send to us for review. We will have a period at the end of the presentation where we will answer as many of these questions as possible in our remaining time. The presentation should be about 50 minutes, which will leave us about 10 minutes to answer these questions. If you're unable to send us a question or have any follow-ups after the webinar, we will provide contact information at the end of the presentation, so you can email us or call us as needed. Okay, so I'll introduce our speaker for the day, Bradley Varhol. Bradley Varhol is the founder and president of EON Products. In 1998, he designed and commercialized the first passive diffusion samplers for VOCs in groundwater, based on the technology developed by Dr. Don Wroblewski at the USGS. Brad also helped develop and introduce the HydroSleeve, another no-purge groundwater sampler, in the early 2000s. In 2014, Brad developed the dual membrane PDB, which is a diffusion sampler that utilizes two membranes to sample for nearly any compound in groundwater. He holds 3 patents for these environmental groundwater sampling devices. Brad also spent 4 years on the faculty of the Nielsen Environmental Field School instructing on passive sampling techniques. He was a member of the original Interstate Technology Regulatory Commission's passive sampling team, and he is currently on the ITRC's 1,4-dioxane, PFAS, and passive sampler technology update teams as they discuss the best solutions to emerging contaminants. Under Brad's direction, EON Products was the first commercial organization to provide passive groundwater sampling education and products to the industry, and EON continues to offer the largest selection of passive sampling devices available today. With that, I will go ahead and let you get started, Brad.
Well, thank you, Chase, and welcome everyone to the Passive Groundwater Sampling Seminar. It is truly my privilege to share our 25 years of passive sampling experience with you today. So let's begin with a quick look at our agenda for today. We're going to walk through some really basic things at the beginning so we can set the ground for talking about the passive samplers. So we'll talk about why do we purge wells. We'll talk very quickly about some monitoring well basics and some historical EPA guidance on purging wells. We'll talk about current groundwater sampling methods. Those include volume and low flow purge and passive groundwater sampling. This will be overviews. Then we'll talk specifically about diffusion samplers and passive grab samplers that are in common use today. And I will show you some testing results and field data that compare these sampling results to those of the more traditional volume and low flow purge methods. And at the end of the presentation, we'll do a recap on passive sampling benefits. Why would you want to use them in the first place? So with that, I will get started. And I will start by first apologizing to all of you who are very steeped in geology and groundwater conditions, but I'm going to start at a very basic level here by explaining what is a groundwater monitoring well. So if you look at the illustration here, we have the ground surface, and we have beneath that what in the drilling language is called the overburden or the dry sediments, and beneath that are the sediments that are saturated with water that is existing in these pore spaces between the sediment grains. And that water moves through the sediment grains driven by hydraulic pressure from a high to a low area. So we have upstream and downstream, basically, if you want to think about it in terms of surface water flow, but water is in fact flowing through the ground. And as it flows, it picks up contaminants or intersects contamination plumes and starts to move those contaminants from one location to another through the aquifer. And of course, that can impact a lot of the use of that groundwater, including drinking water. So if we want to know what the impacts are and we want to know what the contaminants are, we need to have a structure or a way to get a sample. So we build these things called groundwater monitoring wells, and they're usually 2 or 4 inches in diameter. And they're consisting really of a piece of pipe that goes through the overburden, and it acts as a conduit to give us access to the aquifer. So this piece of pipe is usually installed some distance into the aquifer, so we have a good seating there. And then beneath that solid piece of pipe, we have additional pipe that has slots cut in it, and we call that slotted pipe the well screen because it screens out most of the rock and soil particles, the sediments, and it lets the water that's already flowing through the aquifer continue to flow through the well and out the other side and continue on its journey through the aquifer. So we call this the saturated well screen. Now, there's an adage that water always seeks its own level. So when we put the well screen into the aquifer and it becomes saturated, the water level rises within that screen and into the pipe encasing to the same level as it is in the surrounding aquifer. So while we have water flowing through the well screen and constantly refreshing the screen with aquifer quality water, when that same flow encounters the pipe that's installed in the ground, it's diverted around the pipe, and the water inside of the casing can no longer move. So that water becomes what we quickly becomes what we call stagnant. And because it's not moving, its chemistry stops reflecting the aquifer quality of the water. And what happens that makes that not reflect the quality is first, we have interaction with the air in the casing as illustrated by this arrow. And that air, especially oxygen, quickly changes the chemistry. We also have other interactions that occur, those being with the water interacting with the well construction materials, the casing, the gravel pack, and the surrounding environment around the well itself. So for those reasons, we end up with stagnant water that does not represent the aquifer. And if we truly want to sample what the quality of the water is in the aquifer, we have 2 choices. We either have to avoid that stagnant water or it has to be removed. And we have a well-defined process for removing that water. It's called purging. And the EPA has given us some instruction on purging wells and why we do that. This is taken from April of 1996 when the US EPA was commenting and helping to provide guidance on the use of low flow sampling techniques. They told us 2 things. They said it is generally accepted that water in the well casing is non-representative of the formation water. And they went on to say that wells are purged to some extent for the following reasons: the presence of air interface at the top of the water column. You saw that in the illustration. Loss of volatiles up the water column, leaching or sorption to the casing or filter pack, that's the local well construction materials, and then chemical changes due to the local environment. That would be clay seals, backfill, and even surface infiltration in some wells. So we use this purging process that the EPA mentioned, and we have some guidelines around that. And there's really 2 types of purging. There's volume purge, which we'll talk about first. And within volume purge, we'll start with bailing. So everybody knows that a bailer is a cylinder that's empty, that's lowered into the well like a bucket, with the expectation that we can fill it with water and pull it back out again, and we have a sample of the water. But because of that stagnant water, every time the bailer is lowered into the well, it has a bit of displacement. So the water level in the well rises until the bailer starts to fill. And while it's rising, it has a pressure head that pushes some of the water back out in the well screen. Then that bailer runs through the stagnant column and drags down some of the whatever is in there that is not the same as the aquifer, and pushes some of it out through the screen and into the formation. So as we run that bailer up and down, we have this piston-like effect that's mixing the water and moving it in both directions. So if we were to take a sample immediately, we know intuitively and kind of visually here by this diagram that the sample wouldn't really represent the true quality of the aquifer. So in the guidance, it's been determined that we want to remove about 3 to 5 well volumes to ensure that we have a good chance of sampling only well water and not this different water that is in the stagnant area. The other method of volume purging is to use a pump. So in the same manner, we take a pump and we lower it through the stagnant water and put it down into the well screen, and we turn on the pump. Now, the pump is a one-way device, so in this case, we're not moving water in and out of the screen. We're only moving it into the screen and up and out of the well. But you know, there's another adage, and that is that water follows the path of least resistance. And the least resistance in most wells is vertically. So as we turn on that pump, we have a very good probability of pulling the stagnant water or some of it and blending it or mixing it with the aquifer quality water. And of course, again, we're not representing the true quality of the aquifer. You can see that happening because there's drawdown at the top of the well that's indicating the pressure differences. And of course, that's driving this stagnant water and groundwater mix. The other method of purging or sampling the wells is low flow pumping. In low flow pumping, the concept is we still use a pump, we push it down through the stagnant water, but we have the expectation that if we run that pump truly, really slowly at a low rate, we're going to pull water in horizontally from the area where the pump intake is. Well, this proves not to be the case in almost every case. And those of you who have done low flow sampling know that when you turn on that pump and you start to analyze the water with the water quality meter, maybe you're using a flow cell, you know that the water quality parameters, pH, conductivity, dissolved oxygen, those begin to change, and they change fairly rapidly, and they change for a while. And what that change is representing is that we're having a different chemistry of water that's flowing into the pump and out to our flow cell. And that chemistry is often the result, or those changes, the result of pulling in some of the stagnant water that is at the top, or water, in fact, from other areas of the screen that don't really represent what we're trying to sample. So the result here, or the solution, is to pump for a duration long enough until those water quality parameters stay consistent or stabilize over time. And that then represents that we're sampling a single body of water that's consistent, which would be representative of the vast expanse of the aquifer. One other thing that we've learned from the USGS is that as we pump low flow sampling, over time, those flow lines become very similar to those of a high pumped well, and that what ultimately we're representing is a flow weighted average across the screen. And by flow weighted, we mean that we have more contribution from higher hydraulic conductivity, higher permeability areas, and lower contribution from tight areas, if you want to call it that, but it's a blend over the length of the screen. So with that in mind, what are some problems that come about from this volume purging or low flow stabilization? Well, in any case, they're time consuming, and they create contaminated wastewater, this purge water. And every time I mention contaminated wastewater and you think about that, I'd like you to think about PFAS, because today's contaminant of emerging concern, PFAS, or Teflon-related compounds, we don't have a good solution for how to cost effectively and time effectively remove them from the groundwater. So if we are creating contaminated purged water with PFAS, we really have something to think about in terms of disposal. Volume purging can also stir up turbidity, and that's because we are accelerating the velocity of the water coming into the well beyond what its natural flow rate is. We're mechanically changing the velocity and oftentimes the direction of flow. And when we have turbidity in groundwater, we know from laboratory results, we can have bias. A couple quick examples would be metals concentrations and PFAS concentrations. Those contaminants tend to glob onto colloids, and if we have colloids or fine sediments in the well, we're going to increase the concentration measured at the lab unless they're filtered. And we also we raise the reporting limits, so we can't get quite as fine a definition of the concentrations. And of course, these techniques require support equipment that's both expensive and logistically can be difficult to maneuver around, especially if we have high traffic or isolated sites. So the question really is here, can we eliminate purging as part of the well sampling process? Let's go back to the EPA back in 1985 when they were writing their very first guidance on environmental sampling of groundwater monitoring wells. They told us a couple of things. They said the goal in establishing a well purging strategy is to obtain water from the geologic materials being monitored while minimizing the disturbance of the regional flow system. They also said that in hazardous environments, think PFAS, where purged water must be contained and disposed of in a permitted facility, it is desirable to minimize the amount of purged water. So we want to minimize the disturbance and we want to minimize the amount of purged water. So, introduction to passive sampling, which we hope can do both of those things. Let's start with the definition of what is passive sampling. The ITRC tells us that passive sampling acquires a sample from a discrete location, and the key here is that this is done without the active media transport, without moving the groundwater that's induced by pumping or purge technologies. Passive sampling also involves that the sampling device is exposed to the media under ambient equilibrium during the deployment period. So we're not changing the water flow, direction, or rate. So a quick overview on the basics of passive sampling before we get to the specific technologies. Here's our well that we were looking at earlier. So we place a passive sampler into the saturated screen zone where it intercepts the natural groundwater flow, which is constantly refreshing the screen and keeping it in hydraulic connection with the aquifer. By some means that we'll talk about in a minute, the sample is captured in the device. In that process, we do not move the stagnant water, so there's no change in the direction or velocity of the water captured up in the well casing, and we do not move the groundwater. Therefore, because we're not drawing water in from anywhere else, the sample that's coming out of that sampler represents the specific interval of placement. So why would we want to use passive groundwater sampling? Well, we're going to address some of the problems with purging, but let's go down this list quickly. Over the last 25 years, there have been millions of samples taken that have demonstrated that we have both accurate and reliable results using passive sampling. There's no wastewater, think of PFAS again, that's because we're not purging, we don't create the wastewater. It does not cause turbidity because there's a minimum of disturbance when the sampler is installed and then the sampler is left there so that things can quiet back to ambient conditions. The big one here seems to be that we can reduce the sampling cost by 50 to 80%. Now, most of us, when they think about reducing sampling costs, we say, well, why do we need to do that? These companies that are polluting our groundwater and our drinking water, they really need to pay the price to have the cleanup of what they're profiting from. But I have a little bit different perspective on this. I think that the first thing, if we can reduce the cost, is that we're going to encourage compliance for sampling. And to get better compliance, to be able to understand better what's happening in the groundwater, I believe that that's a huge benefit for all of us. The second, which is maybe even more important, is that if we can reduce the cost of sampling, we can maybe reallocate those funds and allocate them more toward cleanup. Because isn't that the ultimate goal of what we're trying to do, is clean up the environment, remediate the environment, and make it safer for us? So sampling doesn't make the environment safer, it just defines the problem. If we can reduce the cost of defining the problem, we can spend more to fix the problem. So the samplers also are very easy to use, and they're highly portable. If you look at the photograph there on the left, that's the photograph of pretty much all the equipment needed to install a passive sampler. We've got a suspension tether and a reel or of some sort, and the sampler itself. So they're highly portable, easy to use, and they're safer because we're not carrying around a bunch of equipment and gear into places that could be a problem both logistically and hazardously. They offer an added benefit in some cases where we have long saturated screens, where we may be able to do some vertical profiling and see what the concentrations and contaminants are at different levels within the well. They're widely used and readily accepted, and I think they're a greener and more sustainable method of sampling because we don't have motors and gasoline and lithium-ion batteries to run our equipment, and we have a very small footprint. So we're probably even smaller than the use of this of tubing that's used for sampling and purging. I missed that one. So today I'm going to talk about the two most common and most used passive groundwater sampling methods. That would be the diffusion sampling and passive grab sampling. In diffusion sampling, we have a water-filled membrane that's lowered into the saturated screen. And once in the saturated screen, contaminant molecules diffuse through the holes in the membrane, the pores in the membrane, into the sampler. And then at some point after some time, those contaminant molecules, they reach a concentration equilibrium with the surrounding groundwater. And now we can remove our sample, and we understand then at the lab what the concentration of these chemicals are in the groundwater. In passive grab sampling, rather than a water-filled sampler, we have an empty sampler that's flat and expandable. And that is placed into the saturated screen in this empty state, so it has very little displacement. And when we want to take a sample, we pull it upward, and it collects a core of the stationary groundwater, and that core is taken through the top of the sampler, which is open. Then when the sampler is full, there's a valve mechanism at the top. It closes, and it prevents any of the water above the sample interval from entering or influence the sample that we've just collected and isolated. Let's talk about diffusion sampling. How does that really work? So in the photographs here, we have a small diameter passive diffusion sampler that'll fit into 1-inch wells and larger. The red mesh around the outside is not the membrane. That's a protective cover to protect the membrane vertically for strength as well as for abrasion resistance. In the picture with the black mesh, same thing. We have a larger diameter sampler. This is a field fillable or factory filled sampler. The membrane is covered with a black mesh for protection, and you can see it's located on a suspension tether for installation. Now, these samplers, the passive diffusion bag or PDB, was initially developed and tested by the USGS and published in 1997. That was Dr. Vrbleski that Chase mentioned. These samplers were introduced then commercially by EON in 1998, so they've been around about 25 years now. There's ITRC studies and guidance very specifically for the use and selection and when not to use a passive sampler. And since that time, there have been over 1 million VOC samples collected around the world using this PDB for VOCs. So let's, ahead of myself here. There we go. So there's more to come. So let's look at the process here. So the PDB, or any diffusion membrane device, is made of a semi-permeable membrane. So think back to high school, and you know that a semi-permeable membrane is a material that has some holes in it, and those holes are called pores, and the pores are sized in a specific manner that they can let some things in and hold back other things. And my simple, easy to understand Brad example is that if you have a screen door in your house or screened windows, those are semi-permeable membranes. They let the fresh air in and keep the nasty bugs out. So in the case of our semi-permeable membrane, we let some contaminant molecules in and we keep other things out. And in the case of the PDB, that would be the water molecules. So the PDB is filled with deionized water, and you know that that is simply H's and O's, hydrogen and oxygen, without the contaminants in it. And this then is lowered into the saturated screen where it intercepts the groundwater flow. And you can see in this diagram here that the blue colored portion, these are the contaminant molecules that are dissolved in the surrounding groundwater. And there are no molecules inside the sampler when it's first installed. But after some time, we have some diffusion into the sampler, as you can see with the shading on the corners of the sampler. And the driving factor for that is the concentration gradient that exists between the molecules on the outside of the sampler and on the inside of the sampler. So natural molecular diffusion is a process whereby molecules of any compound, if they're in a liquid or solid, they tend to randomly and chaotically move around and bump into each other until they're spread out equally within the volume of the liquid or gas that they're in which they're contained. So in this case, the concentration gradient is higher on the outside of the sampler, lower on the inside, and the pores provide a pathway or an entranceway to get into the sampler. So those molecules diffuse into the sampler over time. And after what we call the minimum residence time, the contaminant molecules reach a concentration equilibrium, the same concentration inside the sampler as in the surrounding water. And it maintains what I refer to as a dynamic equilibrium, meaning that if the concentration of those molecules in the well go down, the gradient is reversed and we have a higher concentration in the sampler. So those molecules push outward and come to equilibrium with the lower concentration in the groundwater. If the concentration in the groundwater goes up, then it goes up in the sampler. And we have this living, breathing equilibrium that is maintained within the well. The nature of the sample collected is a time-weighted average representing the last few days at the sample interval. The time weighting is based on each molecule, each compound has its own rate of diffusion. So for example, something like benzene takes about a day to come to equilibrium, and something like vinyl chloride takes maybe 4 days, maybe 5 at the most to come to equilibrium. So we can say that whatever the day we pull out the sampler after it's reached its minimum residence, the sample will always represent that last little few days period of time. Now, standard PDBs have been evaluated early on in their career back in the early 2000s. The Navy conducted some testing in-house where they created a bench test with a test chamber that they spiked with certain VOC compounds of interest. They put PDB samplers into that spiked chamber. They let them have their residence time. They pulled them out and they analyzed the concentrations in the samplers and compared that to the concentration in the chamber that they used as their controls. And you can see here that we have a very close agreement between the gray bar, which is the chamber, and the inside of the sampler, which is represented by the blue color. If you look at the legend or the x-axis on the bottom, you can see the concentration, the very small increments of difference between the two, and you can see that there is no bias in one direction between the sampler and the chamber water. If you look at the second graphic, this is a early on example of a PDB versus baling, and this was conducted by a consultant, Bunnell Lamons in South Carolina. This is a one-to-one data plot. So we take a sample from a well using a baler, and then we also take a sample from that same well at a point close in time with the PDB, and we plot those results as one-to-one pairs, and the closer we get to a straight line, the more those two compare. And in this case, we have a very close comparison here, illustrated by the trend of those dots. And we also have a PDB versus low flow graphic on the right. This is a USGS field study that was conducted in Alaska for quite a number of VOC compounds. And you can see again, we have a very close one-to-one correspondence. So these types of case studies and tests have been done for years and have shown really a very close correlation with PDBs and other methods of sampling in terms of results. There's another type of passive diffusion sampler. Because the standard PDB can only sample for VOCs, it sure did leave a host of other compounds that needed to be sampled, and why not find a way to do that passively? So we developed the dual membrane sampler, and the dual membrane sampler is built on a perforated tube that runs the length of the sampler. Around the bottom portion of the tube is wrapped a low-density polyethylene membrane, LDPE, that is the same material that's used in the standard PDB. It has very small pores, it holds in the water molecule, and it allows VOCs to diffuse into that portion of the perforated tube. At the top portion of the sampler, we use a different membrane, so the two membranes do not overlap. These are both wrapped around a single perforated tube. And this membrane has large pores, and by the way, it can be interchanged, different membranes can be used here. But our standard version has large pores that allow any compound that's in the groundwater to diffuse into the sampler. And once in the sampler, natural diffusion mixes or causes the molecules to mix throughout the sampler. So we have a dynamic equilibrium in the sampler and with the surrounding groundwater. Some test results showing comparisons that have been proven over the years for the dual membrane for other compounds. Lots of people, especially landfills, are interested in Appendix 1 metals. So at some of our Superfund and DOD sites, our consultant, in this case, conducted some testing, and they collected 135 data pairs, so 135 low flow and 135 diffusion-based samples for these Appendix 1 metals. They tracked very closely along a one-to-one plot with an R-squared ratio of 0.94. 1.0 is a perfect ratio. Typically anything in the high 80s or low 90s is considered generally acceptable, and we have a very high score here of greater than 0.94. In the diagram on the right, some data collected at a couple of US EPA Superfund sites for target analyte metals, and also the inorganics. In this case, a little bit larger study, 378 data pairs with an R-squared of 0.96. So what we're showing here is that we have very close correlation to the sample results from low flow sampling and from using the dual membrane passive diffusion sampler. Everybody's interested in PFAS, and I'm certainly making a big deal of it today when I talk about wastewater. There was a US DOD study conducted, and I'm sorry, I can't name the site, but that was at their request, where they sampled for 24 PFAS. There is a publication on this. The site isn't named, but the data, the specific data has been published. 126 data pairs collected, and on the one-to-one plot, we're showing a R-squared of 0.99, which truly is quite an excellent correlation. So we're getting essentially the same results from a dual membrane sampler that we are from a low flow pump sample. Another U.S. government agency that expects to publish their own report soon conducted a study at 28 wells. I had the privilege of being on that site. They collected 70 data pairs that had PFAS hits out of those 28 wells. And we have, in that case, the data was plotted, and we have a 0.98 correlation on 32 PFAS. And by the way, both of these lab methods, we're using method 537M, so the modified version of 537. The state of New Jersey has highlighted several PFAS, PFOA, PFOS, and PFNA, and they've called them priority PFAS. Integral Consultants did some side-by-side field tests for these priority consultants, and you can see the plots are essentially what we've seen in the last two slides. We have greater than 0.98 or 0.99 correlation. But I want to point out one thing. One well was shown to be highly turbid. I think I was told that the turbidity in those wells was 135 or 140 NTU, so fairly cloudy. And in those cases, the results from the low flow sampling method showed a considerably higher concentration of PFAS than did the passive sampling method. And of course, we know from laboratory data and other information that PFAS tends to attach itself to colloids. And if we have unfiltered samples, we're going to artificially raise the concentration of the PFAS in the sample. The other interesting thing about that is that throughout the study that was done here, this same effect exhibited itself, and it caused the reporting limits to actually increase. So we had a kind of a twofold effect, a higher concentration and also higher reporting limits that in one case were above the 13 nanograms per liter state limit. So it's pretty hard to understand what's happening in a well if our reporting limits are higher than our MCOs. So like everything else, diffusion sampling has limitations, and it's right that we point those out. In every case of passive sampling, the sample volume is limited by the size of the sampler that fits the well diameter and screen length. And that would be the saturated screen length. And that's because you're limited to the water in the screen, because the only way to get more then would be to pull the water in, and now you're not passive sampling anymore. So to offset that, there are samplers available that can sample up to 1 liter in volume, or on sites, another approach to this has been to use multiple samplers in the same screen and combine the contents just to get a greater sample volume. It's also a limitation that it takes a minimum, what I call the minimum residence time of 2 to 3 weeks to allow for the well to recover. So part of this residence time is when we put a sampler into the well, we're disturbing the natural flow. We're usually adding, this volume of displacement to the well. So it takes some time, especially in low flow conditions, to recover that well to its natural and ambient flow condition. That's a requirement for passive sampling. And then if we're with a diffusion device, it requires the amount of time for the individual compounds to come to equilibrium. So we know that in every case, we're talking about somewhere between a 2 and 3 weeks residence time, most of which is for the well restabilization. The good news is that there's no maximum time limit. So because it stays in dynamic equilibrium with the formation and the aquifer water, we can install the samplers at one event and just go away for a month, a quarter, a year, or 2 years or longer. And when we come back, the sampler that we pull out of the well will represent exactly the concentration of the water over the last few days. So that means we can install a sampler at one event, and when we recover it, we can put another sampler in, making it ready for the next event. So we don't have a second mobilization. A quick recap: standard PDBs versus dual membrane. Standard PDBs test for VOCs only. It's a single membrane, and they've been commercially available for the last 25 years, since 1998. Dual membranes will test for all compounds because they have two membranes that have different characteristics for diffusion. And these have been available for the last almost 10 years now. Quick kind of photo review of deployment. On the left upper, we have a typical factory-made suspension tether with a polypropylene chemically resistant rope. By the user's hand there's a stamped well ID tag, and the entire suspension with the samplers on it are suspended from the bottom of the well cap, so it's locked in place and out of view. Bottom left is a picture of a PDB that's attached to the suspension tether, ready for installation. And in this case, we make a suspension tether with permanently installed stainless steel rings so that the placement of the sampler is consistent, the tether is reusable, and we just zip tie the sampler over to those rings. So when we pull it out, we snip the zip ties and put another sampler in the same place. The two center photographs are installations of the samplers. The one on the right is dual membrane samplers being installed at an EPA site, and we're vertical profiling in that site. And the discharge of the samplers, the preferred method. All of us have either been kids or have kids, so we've used a juice box. I like to refer to the discharge straw as a juice box straw. We puncture the membrane, and that provides us with a laminar flow into our sample bottle that has minimum air exposure. So that's passive diffusion sampling. What about grab sampling? So the hydrosleeve is a catchy name that most people have heard when they think about or have heard about passive groundwater sampling. The photograph on the left is a hydrosleeve. It's just been removed from a well at a remote location, and it's full of sample water. The photograph on the right shows the top of an empty sampler. So the top is open, and you can't see it because it's transparent, but right under the top of the sampler is a short length of sleeve material that forms what's called a reed valve. So it's a automatically closing valve, and that's what's used to isolate the sample. So hydrosleeves have been accepted and used in every region of the US EPA. Over 1 million hydrosleeve samplers have been deployed because they can test for all compounds. Because with a grab sampler, remember, we're grabbing a whole water sample. And more than 50,000 hydrosleeves have been deployed for sampling PFAS. We make a version of the hydrosleeve out of HDPE, which is a preferable material for PFAS sampling. So hydrosleeves have become the most used passive groundwater sampler in the world. Here's how they work. First of all, that flat sampler, the one in the photograph that didn't have water in it, is installed below the sample zone. So you can see here, we have the top of the sampler, and this is where we expect to get our sample. To collect the sample, the hydrosleeve is pulled upward rapidly on a tether through the sample zone. And by rapidly, we say 1 foot per second, but who really knows what that is, right? So practically speaking, it's about the speed that if you were standing up with your arm straight down at your side, and you kept your arm straight and moved it in an arc to above your head, about as fast as you could do that, that's about 1 foot per second and entirely adequate to collect a sample. So while the sampler is moving upward, the water in that interval is stationary, and the sampler is expanding as it goes around the core of water in that interval. When it gets to the top and the sampler is full, that little reed valve I referred to collapses. It's like the valve in the Mylar party balloons, birthday balloons. So it collapses, and the hydrostatic pressure of the water between the sleeve and the valve holds that shut. So as the sampler is pulled out of the well, it is not influenced and does not capture any of the overlying water layers. So the water itself does not move, so that's an important point. Only the sampler moves. And by the way, I think of this like when I get up in the morning, I put my socks on, and when I have a sock, what is it? It's a tube that's sealed on the bottom. It's opened at the top, and as I pull it up and over my leg isn't moving, but I am capturing my leg into the sock, and that's what's happening with the sampler. So only the sampler moves. Because it's a grab sampler, it's recovering the actual water that's in the well, the aquifer water that's been refreshing the well, and everything in that sample. So if you have dissolved or suspended materials, anything in that interval is captured. And because of the mechanism, because we're capturing the sample and then instantly removing it, what we're seeing is an instantaneous snapshot at the sample interval. So in that respect, it's much like a pump sample in that it represents the temporal or time of the actual sample being withdrawn from the well. Here are some comparative data charts that have been collected here. I don't need to explain how the charts work anymore, but if you look for metals, in this particular case by WSP Parkins Brinkerhoff, we have a 0.96 R squared, a 0.94 for BTEX, inorganic sulfate 0.99. And we have some information collected from some state agencies. In 2007, the California Department of Water Resources conducted comparative studies at 11 wells, and their conclusions are this: the use of hydrosleeves following a standard procedure should produce highly accurate and reproducible data at both clean and contaminated sites. So we don't have any false positives or negatives. Use of the hydrosleeves will save the DWR time and money, and the hydrosleeve should be seriously considered for use by the DWR and our contractors. So the little asterisk there is telling me, did a little research and we found that the California DWR has been purchasing hydrosleeves for their sampling sites and uses them on a regular basis. Quick couple data plots from that particular study. Trace ion data for metals gave us a 0.94, really close correlation. And for physical parameters, which we can collect because we're getting a whole water sample, we have a 0.99 collection. So even if you're not collecting stabilization parameters, you can certainly collect water quality information. State of Kansas did a landfill study, concluded that hydrosleeve results were very consistent with their purge methods. Hydrosleeve provides more accurate results for VOCs, and that was because they weren't aerating the sample. Hydrosleeves for metals were less turbid than the pump samples, and they concluded that the use of hydrosleeves should be approved because it provides consistent and accurate data with many benefits. And the state of Kansas directly purchases, and they have their contractors purchase hydrosleeves for their landfill sites. Just like anything else, hydrosleeves have limitations. The sample volume is limited by the size of the sampler that fits the well diameter and saturated screen length. But again, the good news here is that a hydrosleeve can be manufactured that will hold up to 2 liters of sample volume, or you can use multiple samplers. And of course, all this is dependent on having adequate screen to support that volume. To get 2 liters of water out of a 2-inch well, we need something between 8 and 10 feet of saturated screen. And just a quick side note, if you're doing the new 1633 draft method for PFAS, you're going to need between 1 and 2 liters of water. So if you have the saturated screen available, you can use a hydrosleeve to get the sample. Quick field photos. Here's our technician out in a remote location. And the high point of this is to show that there's very little equipment that's being used. He's got a water level meter, his cooler, and his bag of hydrosleeves to redeploy before he leaves the site. And the photograph on the right is a location with the full hydrosleeve just removed from the well. It's been proven reliable. I said that a few times, but here are some of the documents that have been published to support that from no less prestigious organizations than the USGS and the ITRC. We have research, we have comparative studies, generally agency acceptance and regulatory guidance. Where should they be used? How should they be used? And really, if they should be used on any particular site. More recently, the USGS published a document in 2020 regarding equilibration type passive diffusion samplers, of which these devices we discussed today were part of that study. And I want to point everybody, if you do get a copy of that, there's an excellent chapter 10 discussing how to evaluate data between two different methods of sampling, because obviously we sample by a different method that we're collecting something somewhat differently. And this talks about how to make those comparisons statistically and not. And then New Jersey just recently updated their field sampling procedures manual, which is very detailed and now includes the devices we talked about today, how and when to use them. So general acceptance across quite a number of agencies. Everybody asks, have they been used on my sites or my type of sites? And I can tell you that the PDBs, the dual membranes, and the hydrosleeves have been used on over 50 Superfund sites. They've been used under over 30 DoD sites in the US, and they've been used on federal sites in all 10 US EPA regions. So as I promised at the beginning, here's a quick recap of the passive sampling benefits. I think you've seen that they have some reliable results, and there's plenty more behind the scenes to support that. There's ITRC guidance. They're used in all the regions and on agency sites. We have over 20 years of sampling history now and over 2 million total samples collected. I think we're getting pretty close to over 2.5 million. And they're widely used throughout the world. I think every continent and quite a number of countries are using them consistently. They're safe and easy because they're small and lightweight. They can be transported and shipped easily. There's less gear and equipment to haul to remote sites. With no purging, we have a lower risk of personal contamination, and we also have less problem disposing of contaminated wastewater. They're sustainable, so we don't have the same environmental impact that we have when we have batteries, motors, compressors, the kind of things that have ultimately are going to end up in a landfill or present some type of air or other pollution. And because they're small and highly portable, there's less time at the well in high traffic areas, and that means two things. One, we can get more sampling in, and two, it's safer for our technicians who are out there grabbing the samples. There's economical benefits. I won't go over my speech about why I think it's important, but a study conducted at McClelland in 2005 compared low flow, 3-volume purge, PDBs, and hydrosleeves, and their conclusion was that it cost about $300 a sample for a volume purge method or low flow, and it costs about $65 a sample for PDBs and hydrosleeves. That was in 2005 dollars. We've seen that same type of information repeated over and over again. It's because we can capture a sample in minutes. And by the way, these numbers don't include IDW, and when we add disposal, the numbers get significantly better because we have little to no disposal water. And then we can eliminate, in some cases, the purchase or rental of support equipment. Reduce costs, increase compliance, put more resources available for cleanup. Thank you. These are the resources I used in today's presentation. I'm happy to share them with you if you just send us a note. I got probably a few more than this ultimately. I appreciate that you have all taken the time to listen in, and I'm going to turn it back over to Chase for any questions.
Thank you, Brad. A reminder for everyone that you can go up to the Q&A button at the top and submit a question. I have a couple questions here that I'll ask that have been submitted for Brad to answer, and we'll make sure we follow up with anyone after the webinar that submitted a question that we're not able to get to in our limited time here. So Brad, the first one, can you discuss sampler selection? How do I know which one to use?
Well, that's a common question, and it has a couple parts to the answer. I would say that the first thing you want to do is to make sure the sampler is capable of actually sampling for your contaminants of concern. Both the dual membrane sampler and the hydrosleeve can sample for virtually any compound that's in the groundwater, so that's a pretty easy choice. I would say that the next determination would be that go to the lab and determine what the minimum sample volume requirements that they need to run the method. There's quite a big gap between what labs initially ask for and what they need, and sometimes it's based on the data quality objectives of the site. So a good conversation about what you're trying to do and what the contaminants are, have that conversation with the lab to determine your minimum requirements, and then go back to your field data and rather quickly just do a quick assessment of how much saturated screen you have. If you have 2 feet of saturated screen, you aren't going to get a passive sample that will meet any lab methods. But if you have 4 feet or 10 feet, you're going to be able to do almost any analysis you need. We know that a hydrosleeve can collect 2 liters in a 10-foot screen, and a dual membrane can collect 650 to 750. So is one sampler enough? Do you have to put 2 in line to get enough volume? Those are really the next set of questions. And I think the third thing that I would say is, do you as the user, the consultant, or the project manager, do you have experience or any particular comfort level with either diffusion or grab sampling? If you do, it's a much easier transition to go to something with which you have experience or familiarity. And you also want to keep in mind then, how does that meet the project DQOs? Your turbidity requirements, your sampling requirements. Basically, do you prefer to have grab sampling or diffusion? I think that's in many cases what it finally comes down to.
Thank you, Brad. Another question. If I want to change a monitoring site from low flow to passive sampling, what is the best way to do this and ensure regulatory compliance?
Yeah, this is another one that's becoming more frequent, actually. I think I would take a multi-step approach again. I think the first thing I would do is I would look at the site and project DQOs. What am I trying to accomplish here? And I would make sure there's an adequate saturated screen for the volume for that, getting what I need there for DQOs. So that's something that EON can assist with. If you have basic well data configuration, we can say, here's your saturated screen here, here's the type of sampler. We can kind of work through that, and where do you put the sampler and how much volume can you get? I think the second thing I would do after I was comfortable that I could actually use the passive sampling is I would go to my regulator and I would have a very frank discussion to understand what their experience is with passive samplers and to uncover if there are any specific concerns that can be addressed with, say, with guidance documents or case histories or other users' experience, perhaps even some test data. So, I think the process between the user and the regulator needs to be a seamless one. And I think addressing everybody's interests is the best way to proceed with changing a sampling method. And then as a final option, I think I would consider a small side-by-side test study. I would pick a few representative wells, and I would compare the data like we did in some of those data plots to show how the results correlate to the low flow or to the bailing or volume purge results. I think you could do that optionally in some cases if you have interest and a history of data at a well. So rather than run a field side by side, you might install some representative wells with the passive samplers and compare the data to field data, to historical data, and see how that measures up. And I can also tell you that we have some SOPs written for how to go about those sampling methods, side-by-side tests. So that's something we'd be very happy to help with.
Thank you, Brad. We're running out of time here, but I'm going to squeeze one more in. This was a good one. If it takes time to restore the well to normal conditions, don't you lose any labor savings by having to mobilize 2 times to the site to deploy and then recover?
Okay, I'll try to answer quickly. One of the benefits of using an equilibrium-based sampler is that they can be left in place indefinitely once that minimum residence time, and they're going to represent the conditions close to the time when they're removed from the well. So that would include the dual membranes, the hydrosleeves, and the PDBs. You can install them at one event, and then as long as your time until the next event is more than the minimum residence time, just recover them at the next event. And as soon as you recover them, put the next sampler in for the next round of sampling and just repeat and repeat. Now, there are cases where some wells are sampled for a one-time event or an assessment event. And in those cases, we have a version of the hydrosleeve that's called the speed bag that has some physical characteristics that make it ultra low displacement and disturbing of the water column. And with those samplers, you can readily take a sample very closely in time to when the sampler is installed, so almost immediately after they're installed. So I hope that helps with the mobilization question.
Thank you, Brad. So with that, we will conclude our webinar. If you missed out on part of the presentation or want to share it with others, we will send out a recording of the webinar and some slides in the next few days. Please reach out to us at EON at any of the forms of contact shown on the screen if you have any questions. And thanks again, everyone, for joining today. I hope you have a great rest of your week.